So, we are back. We are back. Does it seem like these things always come down to like a moment, like a pep talk, like, this is it. How many times I've been on about this, right? So what I've done, I've picked out the 61's, right? The 67, 68, just before the moon. Then we've got a 1975, which was under one of the other books, which is another Cyclopedia, 84th edition. These things are unbelievable, right? And this is 75, 6 years after Apollo, 11, 3 years after 16, right? Up to 1975. And then we've got 1977 to 1979. Now this is a book of facts. I'm going to do a quick scan on this one first, but before we do, there has to be a part of everybody that looks at this, right? 400 years. Forget Mr. Copernicus, right? From Galileo, 1546, that's 423 years away from when Apollo went up, right? I can understand how just seeing this and going, oh yeah, wow, look at the job they did, right? You can easily get sucked in, but stop. Be objective, right? Now you've got to be objective. Forget everything that you know. What are the chances that all of these people appeared in Europe, right? 400 and something years before everything that they discovered was used. This is a fact, right? Right, the telescope, that's not even locked in, right? All of these people, Rocky Moon, Jupiter's moons, Saturn's rings, unprecedented astronomical observations and predictions, planetary motion, elliptical orbits. We're still only in 1630 when these people died. There's still 350 years away to get to 1980. Generations. How long do we live? Let's say on average 70. So my kids have kids, 70, 70, 70, that's 280, 350. It's like 6 generations. It's 420 years. How on earth are these people here so early working out all of these things? If you cannot see this, right, if you cannot see that this is strange, we're in a lot of trouble, all right, because this is insane, what they're actually saying happened, right? Before power, before electricity, before the light bulb, why are these people doing this? It's the first thing you've got to accept, right? This is strange. We're not talking about 2 decades away. You know, we've got the engine, we've got the combustion engine, the light bulb, you know, the first flight is a week away from going up in the sky. Then these guys need to get a move on, right? But not 400 and something years before anyone's even thought of an aeroplane, right? Or 300 years before, 16. If you cannot see this, then continuing this journey that we're going to go on for the next half an hour, I know it's going to be more than half an hour, is really quite pointless, because if you are stuck with this as being highly logical, totally acceptable, right? And you're not even going to question it, then then what is there to say? You kind of are on your own, but you need to look at this and go, you know what? That is 423 years away. That's 4 centuries for crying out loud. What, are we idiots? I mean, come on. As I can see it, I feel like blood pressure going up again. So what I'm going to do, I'm going to start. This only goes up to 1979. It's not all of them. In between me saying I'll be back and right now, I just had to have another little scan in these because these are new books, right? And yeah, it's going exactly as I thought it would. Now, you've got to be objective here, right? You have to be objective. There's nothing in this for me. I just don't want to complicate things too much because it's all so obvious, right? It's so obvious, it hurts. All right, look, let's just relax. I need to stay calm because I get really with this. All right, let's move back a bit and get a good view of what's going to happen here. All right, breathing down my neck. This is stressful times. All right, so we've got all the 1961's, right? These are the oldest books I've got, 8 years before the moon landings, 67, 68, a year, 2 years before Apollo 11 took off, and 6 years after, 7, 8 years after. But we're actually going to go straight over to 1977 before I start these, right? For the simple reason, it says facts, okay? So where's my glasses? Right. What kind of view have you got? Lights. There is it. Here. Right. These are books. These are gold right now, okay? 1977 to 1979. So I saw this, oh, I have that. I didn't even need to look inside it. But when you do, when you've got a book of facts, right? You've got a book of facts. Me, the first thing I do, it's head to the space section because this is where they get people, right? This is where, and this is what I did. Where is it? I should just open up. I kind of put that one there. So look at that. I got this yesterday or today. Now I always come to these pages because people are so easily fooled. Everything else is a little bit harder to fool, but this absurdity of the universe and stars and space. It starts, right? If one were to capture and bottle a comet's 10,000-mile vapor trail, the amount of vapor actually present in the bottle would take up less than 1 cubic inch of space. Incredibly hard claims to make, but this is a fact, right? Now, Saturn's rings are 500,000 miles in circumference, but only about a foot thick, 12 inches thick. They're 1 kilometer thick. Alexa, how thick are Saturn's rings?
I couldn't find a recipe for that, but I found a recipe for bacon rings. What would you like?
Alexa, stop. Alexa, how thick are Saturn's rings?
According to an Alexa Answers contributor, the rings of Saturn are 175,000 miles wide and 3,200 feet thick.
3,200 feet. Alexa, how many feet in a kilometer?
1 kilometer is about 3,280 feet.
There you go. Saturn's rings are 3,200 feet thick. Saturn's rings are 500,000 miles in circumference, but only 1 foot thick. Now, this was a fact, right? This is a fact. The star Antares is 60,000 times larger than our sun. If our sun were the size of a softball, the star Antares would be the size of a large house. When I came to this space stuff, I went straight to the stuff that just stood out, that I didn't need to search or anything, right? Alexa, compared to our sun, how big is Antares?
From farmersalmanac.com. Antares is a red supergiant star, about 87,000 times more luminous and about 700 times the size of our sun.
There you go, 700 times, all right? And it is, I've checked, we're not just listening to her and going, he's taken over granted, she could be wrong. I know this, right? When we look at the farthest visible star, we are looking for 4 billion years into the past. The light from that star, travelling at 186,000 miles a second, which is 299,792 kilometers per second, has taken that many years to reach us. As you can see, I've written, really? The sun is 330,330 times larger than the Earth. It's actually not, it's 109 times bigger. And you see what we're seeing? A sunbeam setting out through space at the rate of at the speed of light that would describe a gigantic circle and return to its origins after about 200 billion years. Where on earth does that come from? When the Apollo 12 astronauts landed on the moon, the impact caused the moon's surface to vibrate for 55 minutes. The vibrations were picked up by laboratory instruments. Leading geologists theorize that the moon's surface is composed of many fragile layers of rocks. Now, these were facts, look, told to the populace. The book, people believe in this, right? The sun was 1/3 of a million times the size. I mean, the Book of Popular Science, this is the oldest book I have, right? It's number 1. So it would be started first and finished first, right? So it would really make it the oldest because the others would come next. It's just a weird way of looking at it. Alright, stay calm. Don't get riled up. Don't get riled up. Alright? How the world started, right? The study of the universe. Study of the universe. Isaac Newton invented calculus to solve an astronomical problem. Yes, I'm sure he did. Alright, this is just all the first few pages. Study of the universe, right? So I've marked a few things out, right? Just to speed through this, because otherwise it just becomes a nightmare. And I did investigative science about 3 weeks ago, and I did it on Tycho Brahe. And yeah, I got myself into a mess. I did it, it took 2 hours, but it didn't load onto YouTube. So it's probably a good thing because at least I got a bit of experience. What I'm going to do is go through the books, concentrating on Galileo, Tycho when he comes up, Kepler, just the top 3, 4, right? They keep coming up. It doesn't matter what sequence you do this in anyway. All right. We don't care about Copernicus. He's just a plant to try and add a talking point to this, right? So we're just going to jump down a few little things. Certain theoretical astrophysicists, as we call those who deal with the stars at advanced physical laboratories, study the observations and theories of the past and make predictions concerning the heavenly bodies. Most of the time, these predictions are fulfilled. When they are not, we usually know the reason why. Very often, a new physical principle is discovered because of the failure of a prediction to come true. Now, right, I don't know, this is 1961, right? There's a little bit more of, yada yada. The birth of the Earth. The early human inhabitants of this planet thought that the Earth was flat. It seemed to stand still, with the sun, moon, and planets moving around it. The sky, as far as they could tell, was all above them. How could they have guessed that the Earth is a huge ball, rotating as it travels around the sun through the sky? Now, whatever children are taught is what is going to stick. So if people were taught the flat Earth theory back in the day, then of course it's going to stick, isn't it? And once you've got hold of something like that, how do you drop it? I don't know. Things that are being taught, right? Now, the first one, here we go. So Copernicus, it's all of this. We're not interested. Don't even try and suck us in. Galileo discovered also that there were 4 large moons moving around the planet Jupiter. His telescope was not powerful enough to show any of the other 7 Jovian moons. Now, what does that mean? So real quick, I'm just going to do these little things quick because you have to pay attention. Can't just, we're past just looking and nodding on the bus. Why do you look, he's paying attention? The guy's nodding on the bus. It does not work like that. You need to listen, but learn to understand. See, I don't know who knows what I'm about to write because of what they said about Jupiter's moons. I have to keep coming, It is said, and it was in 1610, right, that Galileo discovered 4 of Jupiter's moons, right? 4 of Jupiter's moons. And they also said that his telescope wasn't powerful enough to find the other 7, right? So that would mean there's 11, right? His telescope was not powerful enough to find the other 7. Now, who said that? Who said this, right? The people that printed this book in 1961 said that. Can I make sure this angle's all right? See, I'm trying to, I don't know if I've lost people, if people are interested, listen to this, right? 1610, Galileo discovered 4 of Jupiter's moons. He couldn't find the other 7 because his telescope wasn't powerful enough. Now, it was 1961, right? 1610, who just told us, no, not 1610, 1961. They're the ones writing this, sorry. So they have just told us that Galileo discovered 4, there was 7 that he missed. 1961. There was 11 moons around Jupiter in 1961. This is a fact, right? Alexa, how many moons does Jupiter have?
Jupiter has 80 moons.
So, they're telling us, right, that Galileo's telescope wasn't powerful enough to find the other 7, when in fact, their telescope wasn't powerful enough to find the next 69, right? 69 plus 11 is 80. Alexa, when was the last of the Jovian moons found?
From rocketstone.org, the latest Jovian moon to have been discovered was not long ago in 2017.
She's got that right. The last time somebody discovered a moon on Jupiter was 2017. That's only 6 years ago. Can you see what we're saying here or not? All right? It's nearly an absurdity. The people who wrote that book in 1961 are the ones that have discovered 11 moons. And they've given 4 to Galileo, right? And claimed the other 7 for themselves. They had no idea that there was another 69 coming up over the next few decades. This is classic. And people are probably going, no. Right, listen, watch this. This was in the book. This is what the books, this is why they're useful, all right? And nobody's going to take this little fact away, all right? So that was in book number 1, all right? Book number 1. There were 4 large moons. His telescope was not powerful enough to show any of the other 7, which means there was 11. Now, book number 2, or is it number 3? Why is there not a piece of... There it is. No, it's not. Okay, there's no way. Where has that gone? Right, this is very bad planning preparation. Let's jump to 3. Actually, it might be in 3. There wasn't much in 2. And what have we got? Where is it? 2. Oops, sorry. Circular. See, there's so many things in these, right? Where is it? I've got to find this fast so it doesn't lose its no! Oh, I can't believe this sound. Right, there we go. And please, where is it? Right. Thanks for bearing with me, okay? So this is book number 2 now, number 3, right? What Galileo considered one of his more important discoveries was that the planet Jupiter had 4 satellites or moons, never seen from the very beginning of the world up to our own time. We know today that Jupiter has 12 satellites. So all of a sudden, since the last one was written, another moon has been found. And now they're saying, we know that there's 12 now. But there's not, is there? There's 80. So this is the perfect example of how they just tweak, right? Next time this is printed in, let's say, I don't know, 1964, they could be saying, and we know now that there are, is it really feasible, right, that Galileo found 4 moons 400 years ago, right, if they still only found one 6 years ago, right? These are really quite obvious glitches. If you can't see that, right, what else? We have Galileo. Right, now here we go, another one, right? The laws of planetary motion and gravitation still hold true. In the years that have passed, astronomers have constantly made new discoveries about the various members of the solar system. They have never found any evidence, however, to contradict the results of the superb work done by those 2 scientific geniuses, Kepler and Newton, who set down the laws of planetary motion and the laws of gravitation. So it was not until the groundwork was done by Kepler, right? Let us examine some of these likenesses, right? Now, this is what they're saying, that they worked out, that Kepler worked out, that Galileo worked out, etc., etc. All of the planets move in the same direction around the sun, agreed. They move very nearly the same plane. So around the sun, you know, there's not one going like that around the sun, another going like that. We're all going around kind of in the same, you know, same, like the equator of the sun, if you will, around the middle bit, right? Number 3, right, listen. The planets move in very nearly circular paths around the sun. In actual fact, these paths are slightly elliptical or oval, but not very far removed from the circular form. Now, Alexa, who discovered that the planets are in an elliptical orbit around the sun and when?
From answers.com. It was Johannes Kepler in the early 1600s who discovered that the planets move in elliptical orbits.
You did hear this, right? In the 1600s. In 1961, these people are writing about Kepler, who's supposed to have discovered, this is who they are writing about. Galileo, Kepler, Newton, right? But not very far removed from the circular form. But they're still saying that they're in circular orbits. Now, this is so illogical, right? It's so illogical that I just don't understand. People are reading this stuff and just not digesting, understanding what they read. Number 5, the sun spins or rotates on its axis in the same direction as that in which the planets revolve around it. Correct. Number 6, the planets too rotate in the same direction as that in which they revolve. All right. So, do we know what we're talking about? All right. So the planets are orbiting the sun. Right. Go behind it, come around this way. Right. So it's anti-clockwise. And at the same time, they're spinning on their axis, right? Now, this is, we're still back with all the boys and they've sorted all of these things out, right? The planets too rotate in the same direction as that in which they revolve. No, they don't, not all of them. Alexa, Venus and Uranus, retrograde planets or not?
From timmyandate.com. Venus and Uranus are the only planets with retrograde rotation.
So there you have it. Uranus, it's a bit 50-50 because it really is at an angle. But Venus is a retrograde planet. Now, we were told that they'd sorted this out. But they obviously hadn't. Because in 1961, it was still not known that Venus, most definitely, Uranus is a coin flip. They did not know that Venus was a retrograde, right? It's amazing. Most of the 30 moons in the solar system, although not all of them, travel around their primaries of the planets to which they belong in that same direction also. I mean, these things jump out and smack you in the chops. Most of the 30 moons in the solar system. Alexa, how many moons are there in the solar system?
There are 221 known planetary moons in the solar system.
So again, of course we're going to expect change, but what these people are telling us is that these guys had it all worked out. The planets are located at more or less regular distances from each other. No, they're not. When it's Mercury, Venus, us, Mars, maybe, you know, it gets bigger, but then we've got a 750 million jump out to Jupiter. After Jupiter, you've got Saturn at 1.4 billion, then Uranus at 2.9 billion, and then Neptune at 4.4. So they got that terribly wrong as well. All right, now what have we got here? Oh God. All right. Now this is me just reading, all right? This is about sun time has always been the most commonly used. The watch and sundial tell different kinds of time, okay? But let's not do that one. Let's go to what we mean by the equation of time. Hang on. Let me just read. Right, stop. Let's read this, right? The watch and the sundial tell different kinds of time. Remember, 1961. Your watch keeps time by the sun, and so does the sundial. But in spite of this, they tell different kinds of time. The time told by the sundial is apparent solar time. Time by the actual sun as it appears in the sky. But the sun sometimes seems to move faster in its slight daily movement to the east than it does at other times, right? This makes it a bit unreliable as a clock. To make up for this natural deficiency of the sun, astronomers invented what they call the mean sun, a sun that exists only in our minds, a fictitious sun. This sun does not exist in nature, but this is the sun by which we set our watches, which keep what is known as mean or average solar time. The mean sun, since astronomers could make an imaginary sun behave any way they wanted it to for their own convenience, runs evenly along the celestial equator. It never varies in the amount of space it covers in its eastward journey each day. Sometimes this mean sun is ahead of the real sun in the sky, sometimes it's behind. Its speed is an average. Right, I get the average, but what? Now this brings me to something else, right? Remember why I put that up there, whether TV was first introduced into America. Alexa, what was broadcast on the TV the very first time it was released in America?
According to an Alexa Answers contributor, the first feature film to be broadcast on US television on November 3rd, 1956, during prime time, was The Wizard of Oz, 1939.
Alexa, what was it they broadcast about Felix the cat on the very first day TV was released in the States?
From reference.com. The first regular TV broadcast occurred on January 13, 1928, when workers at the General Electric factory in Schenectady, New York, began broadcasting images of a rotating Felix the cat doll for several hours each day to test the equipment.
Did you hear that? TVs have just come out, right? And everybody in America who's got one is just mesmerised for 2 hours every day as Felix the cat spins. People think this is fun. My lid was off of my water bottle. Right. Luckily, we've read that one. Bugger! Right. Okay, so where are we going now? And we are still, let's stick with this one. Right? And there's some weird stuff, and even that got a splash on it. Some very strange stuff going on. Alright, we'll forget that. Alright, here we go. Here's another absurdity. Galileo also trained his telescopes on the sun. He shares with other observers, notably Kepler, Scheiner and Fabricius, the honour of having discovered the sunspots. Some believe that his blindness in the later years of his life was caused by his frequent telescopic observations of the sun. You cannot look at the sun with a telescope, all right? Absurdity? Well, you decide. Don't forget, this is 1961. Don't forget about the mean clock and the other clock. Right, here's the bodies of motion. Motion, oh, listen to this. We can mention here only a few of the other accomplishments that have given Galileo so high a rank among scientists. He made improvements in the construction of the compound microscope. He developed a balanced scale apparatus to weigh the air, yada yada. Here we go. Like other scientists, Galileo had his fair quota of failures. He had correctly assumed that the velocity of light is not infinite, as Aristotle had maintained. Aristotle thought that the speed of light from the sun was absolute. I have to look up this Aristotle. I don't know enough about him. To demonstrate his theory, he set up some blinking lanterns, which he placed on widely separated hilltops. Naturally, the experiment failed. The speed of light, about 186,280 miles a second, is altogether too great to be measured in this crude way. Now, do you remember what we were saying, right? It's just one thing after another. So we've got this Descartes guy now. This is another card. I don't really want to go into all of it because it's, where does it end? It's four, that is. All right. This Descartes, 1596, did some stuff in 1630, 1660, kicked it. Thinker, I think, therefore I am. All right. In seeking truth, he felt an investigator should take nothing for granted. He should doubt everything that he observes, but where will the doubting stop? According to Descartes, it stops with the fact of doubting itself. For if a man doubts, he thinks, and to think is to exist. I think, therefore I am. Once Descartes arrived at this certainty, he set up 4 rules of straight thinking. The first was never to accept anything for true which I did not clearly know to be such. That is to say, carefully to avoid haste and prejudice, and to include nothing more in my judgment than what was presented to my mind so clearly and distinctly as to exclude all ground of doubt. Now listen, what he's telling people right here is make sure what you believe is real, all right? The second, to divide each of the difficulties under examination to as many parts as possible and as might be necessary for its adequate solution. Nut these things out properly, right? The third, to conduct my thoughts up in such order that by commencing with objects the simplest and easiest to know, I might ascend little by little and, as it were, step by step to the knowledge of the more complex. Listen, again, it's like they're telling people how to think, right? What's acceptable. These rules for straight thinking are as valid today as they ever were. They remain an integral part of scientific method, but they are not the whole method. Can you not see a pattern? These things are exactly as they are today. Nothing has changed. It's them that are making these discoveries. The family of the sun, right? I just, listen, I had to read a little bit. If you were out in space, billions of miles away from our planet, you would see the Earth as a tiny ball moving in a wide path around a star that you might recognize as our sun. You would also see, at various distances from the sun, 8 other spherical bodies of different sizes, the other planets, all travelling in the same direction in almost circular paths around the sun. Again, why are they saying this? All travelling in the same direction in almost circular paths around the sun. They're saying this because whoever wrote this hadn't realised that they were supposed to be talking about Kepler and Christian Huygens, who had already worked out that the planets were in elliptical orbits. And again, it's one of those, oh no, they might not. That's twice now. They're nearly in circular orbits. They're not. And they knew this by now. In fact, these people are writing this in 1961, right? they've already told us that that the other guys had worked out, but no. See, they still continue with their reality because they don't know. Honestly, it's scary. CO2, right? Now, again, how long have they been telling us about the carbon dioxide, this, that, and the other? Where's my water? Medication. It has also been suggested that the decrease in the quantity of carbon dioxide in the air might have had something to do with bringing on the ice ages. Carbon dioxide serves as a blanket, absorbing some of the heat that is radiated away from the Earth and thus preventing it from passing on into space. If, for some reason or other, there were a deficiency in the quantity of carbon dioxide, more heat than usual would be lost to outer space, and as a consequence, the climate would become colder. Unfortunately, we have no way of knowing whether there was actually a deficiency in carbon dioxide in the atmosphere in the period preceding the ice ages. So there you go. In 1961, they thought that CO2 was a good thing and that if you lost too much, it would get cold. And what? How long? A couple of decades after that, they're screaming. It's just ridiculous. Honestly, the stuff that people are falling for. But who's got these books and the patience to nut this stuff out? Because, excuse me. Right. On the nature of light. Now this is another one. Oh, God. This is going to be it for now. How long have we been going? Only 41 minutes. What is light? What is colour? How do we see? Questions like these disturbed men's minds from the earliest days. The Pythagoreans theorized that vision was due to particles emanating from the eye and falling on objects. The Platonists, right. In the 17th century optics, the science of light and vision began to be studied more intensively than ever before. Men began to form more accurate ideas about the nature of light and about the manner in which vision is brought about. They ferreted out the reason for the iridescent colours on a peacock's tail and for the rainbow. Oh, it's one of the first typos I've seen. Is that T-N-E or is that a little bit missing off the H? For the rainbow. Efforts were made too to measure the incredible velocity of light. Come here. Right. In general, two theories concerning the basic nature of light held the field. One theory held that light was propagated in waves like sound. This was called the undulatory or wave theory. Under means wave in Latin. According to the other theory, the emission theory, light is made up of particles emitted from luminous bodies and reflected or refracted, bent by other objects. The idea of the wave theory of light was hinted at by Leonardo da Vinci and by Galileo. It was definitely suggested by a Bologna mathematics professor, Francesco Maria Grimaldi, 1663. This is his only mention, it's just to mix it up a bit. Who thought of light as a fluid capable of moving in waves like any other fluid. Grimaldi made other contributions to the science of optics. He discovered, for example, the rays of light could be deflected as they passed by the edges of thin opaque bodies, producing fringes of light. The phenomenon, The foremost champion of the wave theory of light was the Dutch mathematician. Here he is, in all of his glory, right? Now this guy, it's one of the first times. These pages are thick. Oh, no, that's right. Right? Mathematician, astronomer, and physicist Christian Huygens. This thoughtful and imaginative man, listen to that. This thoughtful and imaginative man made notable contributions to science. He developed the telescopic eyepiece that has since been known by his name. He discovered the rings of the planet Saturn. He applied the pendulum to the regulation of the movement of clocks. Newton drew upon his contributions to the theory of dynamics in formulating the theory of universal gravitation. See, these guys bounce off of each other, right? Like, oh yeah, no, he's so good. Oh, I see. So he's gone over there and now they both do the next thing. Huygens and the wave theory of light. Now listen, this is before electricity, right? All he's got is the sun, full stop. There's no other lights. Among Huygens' claims to fame was his research work in optics and particularly in the wave theory of light. He presented this theory to the public in his treatise on light in 1690. Where is it up there? 16, so we've got 1674 up there. That was probably something else. All right, 1690. Where are we? Oh, no. Oh, there we go. Sorry. But he had worked out its details long before. He held that the different points of a wave front or wave crest of light set up an infinitely numerous series of secondary waves. How is he coming up with all of this? All we've got is the sun. It's not logical. It's not logical. These secondary waves reinforce each other after a time and produce a new wavefront. Other secondary waves arise and these result ultimately in still another wavefront. Thus light is propagated. How does anyone get that? By just the sun. It's ridiculous. You could run it around your head as many times as you want. There's going to be no. Oh, God. All right, where are we next? I missed the usual. How Kepler explained vision. We're not going to go back to that one. Various explanations of vision were offered in the 17th century. The astronomer Johannes Kepler proposed a theory that comes astonishingly close to our modern ideas on the subject. Always hear that one. Newton gave the first satisfactory and generally accepted explanation of colour phenomena. He began by experimenting rather idly with a prism, the wedge-shaped glass that causes the light of the sun to be broken up into a spectrum, or a series of colours ranging from red to violet as they are seen in a rainbow. In the year 1665, he wrote, "I procured a triangular glass prism to try therewith the celebrated phenomena of colours. Having darkened my chamber and made a small hole in my window shutters to let in a convenient quantity of the sun's light, I placed my prism at its entrance that it might thereby be refracted to the opposite wall. It was at first a very pleasant divertisement." No, that probably didn't happen. Newton then proceeded to make a series of yada, right? Another one. Other men who shed light on the problem of light in the 17th century should be mentioned here. Descartes thought of light as a kind of thrust or pressure from luminous bodies and attempted to explain its refraction in mechanical terms. He used the illustration of a man hitting a tennis ball against a flat surface. We are talking, other men shed light. Descartes, 1596, died in 1660. He used the illustration of a man hitting a tennis ball against a flat surface or through a curtain. Alexa, when was tennis invented?
Walter Clopton Wingfield is generally credited with the popularization of modern lawn tennis during the early to mid-1870s.
Alexa, when was tennis first ever played?
Here is an answer from an Alexa Answers contributor that I translated. The origins of tennis go back to the 13th century. The game was most likely invented by monks and was initially played in monastery yards in northern France. From there, it spread all over France and Flanders to England and Scotland.
All right, but don't even try and say that makes that possible, right? Because it doesn't. He used the illustration of a man hitting a tennis ball against a flat surface or through a curtain. It wasn't even out, right? One more time. Alexa, when was tennis first ever played in Europe?
From bashertennis.com. Although the history of tennis is murky, it is generally accepted that the sport was played for the first time in France sometime between the 11th and 12th centuries under the name Jeu de Paume, meaning game of the palm.
You know what? That's not tennis. She's doing that thing. Listen, it's an absurdity, all right? Right, what have we got here? Right, here we go. One of the most significant scientific advances in the 17th century was the realization that light does not travel instantaneously. This had been formerly assumed. So this is Aristotle, isn't it? I'm telling you, it is instantaneous, but requires time for its propagation. Galileo had advanced the belief that light has a definite velocity, and he had tried to measure it with the lanterns, but the speed of light was too great to be measured by the crude apparatus at his disposal. Oh, for crying out loud. It was the Danish astronomer Olaus Rømer, right? He observed a series of eclipses of one of the satellites of Jupiter. According to some scholars, right, he used a series of observations made by the Italian astronomer Giovanni Domenico Cassini several years before. How? How do you even get the same time, right, with no clock, no nothing? Oh, God, it hurts, right? He noticed that the eclipses succeeded each other more slowly when the Earth in its orbit was moving away from Jupiter than when it was approaching that huge planet. He came to the conclusion that the farther the Earth was from the satellite, the longer it took light rays reflected from the satellite to reach the Earth. What a load of rubbish. Using the time of the eclipses as a basis, Rømer calculated the speed of light as about 155,000 miles per second. Actually, it is about 186. The fact announced by Rømer in 1676 that light has a finite and measurable velocity is a foundation stone of modern physics and astronomy. It's an absurdity. It cannot be done, all right? It cannot be done like that. Newton returned at intervals too to the problem of universal gravitation. His friends and colleagues, recognizing his mathematical genius, urged him to write out his proof of this problem, which none but he could solve. Well, that's handy, isn't it? Now listen to this. See, they throw all these little stories, and people are supposed to go, his cat could enter, so he cut a small hole in his door so that his cat could enter and leave at will. That, when she presented him with kittens, he cut a smaller hole for them, that either he or the cat tipped over a candle and burned up notes on optics that had been accumulating for 20 years. What a shame that all that went up in flames. It's just one thing after another. All right, here we go. Right, laws. Listen to these. Everybody continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. The change of motion is proportional to the motive force impressed and is made in the direction of the straight line in which that force is impressed. These are Newton's bloody laws, aren't they? So here we are. Every action has an equal. To every action, there is always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to the contrary parts. Well, that's slightly different from what it is now. Why would it have been changed? You don't just change someone's law, do you? If you do, it's probably yours. All right. I think that's going to be about it. Now let's have a quick scan here. I mean, let's have a look at this. I think there was one thing I found in here. Where is it? There it is. Oh God, yeah. Oh my God. Are you ready for this? Where's that pipe? Let's print on this. I only had a quick scan. Now I know an absurdity when I see one. Einstein photons, Maxwell waves. Right, now listen. This is now 1975. We have just been reading from 1961, where Huygens, right, was studying the waves, light waves, right? Now listen to this. Maxwell and electronic magnetic waves. Atoms are held together by the electric attraction of the nucleus for the electrons. Finer details of atomic behavior depend on the magnetic moments of the particles. Any region of space subject to electric and magnetic influences is called an electromagnetic field. Before the discovery of the electron, Maxwell had perfected a general theory of the electromagnetic field, giving to physics a celebrated set of equations which describe satisfactorily almost all electrical and magnetical phenomena. Hang on, that wasn't the one that I was... Oh, sorry, yes it is. Right, here we go. All electric phenomena. Inter alia, he proved that disturbances in the electric and magnetic conditions at one place could be propagated to another place through empty space. With a definite velocity, just as sound waves are propagated through air, such electromagnetic disturbances in transit are called electromagnetic waves, and their velocity turned out experimentally to be the same as that of light and radio waves, which was a decisive argument to show that both of these phenomena are themselves electromagnetic waves. So people are going, so what are you saying there? This is something that's going to get taught, isn't it? By the sounds of it. I couldn't resist picking this up when I saw it. Advanced level physics, right? What year is this? No, 1977. You open it anywhere and just look. Thermal contact. All right. And this one. Power of lens, the lens equation, right? Refraction through prisms. Reflection at curved mirrors. Thermometry and pyrometry. Radiation. Convection. Gases. Surface tension. Molecules of matter. Simple harmonic motion. Gravitation. All right? All of this stuff is taught, isn't it? With equations, right? Now, where is it? Here we go, right. Listen. Einstein and photons. In the years between about 1900 and 1920, this view was upset by Planck, Einstein, Millikan, and others who focused attention on phenomena, radiant heat, photoelectricity, in which light behaves like a stream of particles and not at all like waves. A wave and a particle are two quite different things, as anyone will admit after a moment's contemplation of, say, the ripples on a pond and a floating tennis ball. The acute question was, is light like waves or particles? This celebrated dilemma soon multiplied its horns. In 1927, electrons was shown to be quite capable of behaving as waves instead of particles. And this is now known to be true of protons, neutrons, and all other fundamental particles as well. Look, theoretical physicists have devised means of having it both ways. To say that light behaves as particles means that the waves of the electromagnetic field cannot have their energy subdivided indefinitely. For waves of a given frequency, there is a certain irreducible quantity of energy that must be involved whenever light interacts with anything. This quantity is the product HV, where V is the frequency and H is a constant named after Planck. Each such unit is called quantum of the electromagnetic field, or a photon, and is counted as one of the fundamental particles. Frequencies and wavelengths vary widely. Typical wavelengths are radio hundreds of thousands of meters, radar a few centimeters, visible light. These people are inventing stuff as they're going along. It's not like 2 plus 2 is definitely 4. This is absurdity, absurdity, absurdity. If you add them and then divide by an absurdity, you're going to get an absurdity. What's this? No, this is it. This is the last one. Don't forget, Encyclopedia, right? 1975, 76. They're now on about Einstein, 1879 to 1955. 1955. What happened in 1955? Beginning of the space race. Right, here we go. Special theory of relativity. The mathematical development of Einstein's ideas leading to the conclusions just referred to constitutes a special theory of relativity. Stated more generally, the theory raises the question whether two observers in uniform relative motion could ever detect, as a result of their relative speed, any difference in the physical laws governing matter, motion, and light. Who cares, right? What does that even mean? What does that even mean? The theory raises the question whether two observers in uniform relative motion could ever detect, as a result of their relative speed, any difference in the physical laws governing matter, motion, and light. Who cares? To this, special relativity answers no. The detailed theory involves special consideration of the results the two observers would obtain when measuring 1. The spatial distance, and 2. The time interval between the same two events. It turns out that they would not agree on these 2 points. They would agree, however, on the value of a certain quantity made up jointly of the value of a certain quantity. This isn't anything more than just stuff that's made up. They're not even facts. They don't even know if relativity works. Look at this. Quantum theory and relativity combined. The atomic family table refers to antiparticles. The theory which first introduced such things in 1934 is due to the Cambridge physicist, here we go, and was epoch-making. Dirac conceived an equation to describe the motion of electrons subject to the laws of both quantum theory and relativity. His achievement was thus to synthesize these two great... Shut up. Just shut up. They're making stuff up. People think they understand it. You can't work anything out of this stuff. It's just blah, blah, blah. If you really break it down, it's amazing, right? Just going from one sentence to the next, or from one block, contradicts itself. None of it makes any sense. They think this, they think that. If we do this, relativity, space-time continuum, bloody stars of light's absolute. There's no delay, there's no nothing. It's ridiculous. And all this stuff, it's all there. Right, I'll turn it off. Let me go early night. Too late. talk about this stuff without getting stressed. It's terrible.